Good morning, PCS members and friends, to our today's IBS PCS seminar, and good evening to Professor Jing from Penn State University, who is our today's speaker. And I would like to invite our scientific host, Moonjip, to introduce our speaker. Please, Moonjip.
Okay, so thanks, Tilen, for the introduction. So today I invited Professor Jing from Penn State University. So he did a bachelor degree from Nanjing University and got master's and PhD from Rensselaer Polytechnic Institute from state of New York. And then he did a postdoc in Harvard University and got tenure. He actually moved to the North Carolina State University for his faculty position. And I think he recently moved to the Penn State University 2020, right, Yunjing?
Yes, 2020, yeah. Just before the pandemic.
Okay, so actually this is a very interesting talk, I think, because we actually do not usually invite people from engineering discipline, but I think he's not only like he's not only innovator in the engineering discipline, but he also does fundamental research in the physics. So today I invited him as a speaker, and I think he will gonna talk about this bilayer phononics and photonic graphene and new playground for twistronics. So please, Professor Yunjing, you may start your talk. Yeah.
Okay, thank you. Thank you very much, Moonjip. Thank you for inviting me to give this talk. Actually, just a few minutes earlier, I mentioned to Moonjip that I'm a little bit nervous today because this is my first time giving a talk to the audience of physicists. So my background is actually not physics. I got my bachelor degree in electronic engineering. I studied a little bit of physics, but I never did good in physics classes. So, anyway, I went to the US to get my PhD in architecture acoustics. So actually, my PhD is in architecture. Then I went to Harvard Medical School to study biomedical ultrasound. I'm still doing research on biomedical ultrasound. And then about the time in 2011, acoustic nanomaterial became a very, very hot topic at the time. So I got into physical acoustics. And then it's maybe about 2015, that's when phononic crystal and topological physics got really hot. So I got into that area. And recently, and I did some research on bilayer, phononic and photonic crystal. So I'm going to talk about our recent work on this topic today. So first of all, let me, for those of you who are not familiar with Penn State University, here what you're looking at is, this is Pennsylvania. Okay, so this is Philadelphia, this is the largest city in Pennsylvania. And this is Pittsburgh, the second largest one. We are here. So I think when the state of Pennsylvania decided to create the flagship university in the state, they decided to look at the map and they just draw two diagonal lines and see finding the center. So we are almost exactly at the center of Pennsylvania. So we are about 3 and 4 hours away from New York and 3.5 away from Philadelphia. But the city itself is called State College, and it's very, very nice university town. So very peaceful, very, very good place for doing research. And Penn State is not best known for research. It's actually, most people know Penn State from football. So I don't know if any of you watch football, but this is our stadium. It's called Beaver Stadium. It's actually, I think it's a top three, one of the largest stadiums in the US. So it's huge. You can actually see the stadium very clearly from the sky. So every year we have this game called the Penn State Whiteout. So everybody would just wear white clothes, and it's very, very insane. So I have to maybe just play a very, very short video. So So of course, this is before pandemic. I think actually last year we got back to normal games, but I've never been to one before because there's so many people there. So I think that's about Penn State, and a little bit about our research. So my lab is called the Sound Innovation of Nanomaterials and the Biomedical Acoustics Labs, the SIMBA lab. It's the same SIMBA as the SIMBA in Lion King. This slide shows the kind of research that we do. The two figures on the left are related to biomedical ultrasound research. So the top left shows we're doing numerical modeling of wave propagation. So we have done many years of research on developing new algorithm to numerically to model ultrasound propagation in biological tissue. And the bottom left figure shows an image from a photoacoustic imaging. So we're using photoacoustic effect to generate medical images for blood vessels. And the two figures on the right, the one on the top is phononic crystal. So this is actually a figure we created for the bilayer phononic crystal. We're actually looking into the space between two phononic graphene, this is structure what I'm going to talk about today. And the figure on the bottom right is a elastic metamaterial. So we build this ultralight, very porous material that have band gaps, so you can actually reduce the propagation of vibration. So you can suppress vibration at certain frequencies. Okay, so what I'm going to talk about today is related to the research on the right-hand side, especially the one on the top right. So I would like to first acknowledge my student Yuancheng Deng, who has been working on phononic crystal for many years. He's going to defend his dissertation in the summer. And Murat Vulic is a postdoc who has been working with me since 2018, and he did all the heavy lifting for the elastic phononic crystal as well as the photonic crystal. So let me start with a little bit background. There's a analog, very interesting analog between condensed matter physics and classical waves. And there's actually a very nice paper that gives a good introduction on this, published in Reviews of Modern Physics in 2001, written by Jay Maynard. Jay Maynard is also a retired professor at Penn State Physics Department. So the idea is that if you look at time-independent Schrodinger equation, which I know very familiar with, the solution here is has this form, right? E2 negative I E over H bar T, right? Now, if we look at the time-independent acoustic wave equation, which is also known as the Helmholtz equation, we see they have very, very similar form. Okay, so in this equation, we have the pressure. This is related to the eigenfrequency of the wave, acoustic wave. And this V sub 1 has something to do with the function of the speed of sound. So speed of sound is not uniform, right? It's a function of space. But the solution of this function goes like this: is E2 I omega t. So if we compare this E2 I omega t and this E2 negative I omega t and this E2 negative I E over H bar t, you can see the analog lies in that in quantum mechanics, we have the energy, which is capital E. In classical wave, especially in acoustics, is the equivalent, the counterpart of energy is the frequency. Okay, so for example, in this graphene here, you can see the Dirac cones at the zero energy level. And you can, in acoustics, you can create almost the same behavior. You can also have this Dirac cone at K point. And in this, depending on how you design the structure, you can find this Dirac cone at a certain frequency. So in our case, it's the frequency rather than the energy. So this analog was actually recognized many years ago.
I'm sorry. Can I ask you a question?
Yes, please.
Is it omega squared, which is the corresponding quantity to the eigenenergy E because I thought that when you solve the time-dependent one, which you didn't show us, you have a second derivative with respect to time, right?
Yes, there's a second.
And so that will give you an omega squared, and that is the thing which we should compare to E. So it's not omega, but omega squared. That's how I was trained. So tell me if I'm wrong or right.
Yes, in that, if you look at the right, so this Q actually Q square is related to omega square. But I'm just looking at the the solution here, which is e to I omega, which is the harmonic solution.
Okay, now I'm puzzled. You show us a time independent equation, but you show a time dependent term below it. What does it mean?
So yes, you start off with the time dependent wave equation.
Right.
Then you assume that okay, the time dependence follows this form, which is e to I omega t. Right. Then you take this solution into the time dependent wave equation to arrive at this time independent wave equation.
Okay, where's omega squared or omega in this top equation?
In this one here, is embedded in this one.
What is it?
This is the think of this as
no. How is Q1 depending on omega? That's my question.
So this is equal to think of this as K. Q1 is think of this as K, and K is equal to omega over C. C is some kind of effective speed of sound in that structure.
So it's omega squared which stands there.
Yeah.
Okay, but then on the left-hand side, I don't understand. By the same logics, are you telling us that in the Schrodinger equation you get in the time-independent Schrodinger equation your Q squared is what? How is Q now depending on E in the Schrodinger equation?
How is what? So I'm sorry. How is?
Yes. What's the dependence of Q on E?
Well, okay. So I can go back to this paper. It's already in the paper. I don't remember at the moment.
I think it's just E. I think it's just E because the Schrodinger equation is a first order derivative with respect to time. So you can only get either, as we all usually learn. So what I'm just trying to say is that the frequency of your acoustic waves, omega, the square of that frequency is what we should compare to the energy of a usual Schrodinger equation.
Well, okay, so I'm 100% sure the analog is between E and omega. I'm not sure how I can address your.
Okay, let's talk later about it.
Yeah. These two equations are from the paper, so we can discuss afterwards. So as I mentioned, the analog was recognized back in 1993, so many years ago. So this group did a study on a so-called phononic crystals. They created this composite material made of aluminum rods in nickel, and so it's like they periodically repeat this unit cell, and they found that you can create a band gap. So if you calculate the band gap, calculate the band structure, you have this sort of narrow but omnidirectional band gap here. So that's the first demonstration of phononic full band structure. And 2 years later, someone found there's a sculpture in Spain. So they went there, and it's a pure, right? And so they went there and they did acoustic experiments, and it turns out that you also have band gaps. It's a partial band gap. I don't think it's omnidirectional band gap at a certain frequency. So these peaks correspond to sound attenuation. So they are inside the band gap, basically these frequencies. So that's kind of what people was focusing on maybe 10 years ago or 20 years ago, which is basically just a band gap. Now, recently there has been a huge amount of attention in combining phononic crystal or photonic crystal with topological physics. So on this slide, I'm showing you some very representative works. For example, the acoustic churn insulator, which takes advantage of the quantum Hall effect. So they use a flow to break the time reversal symmetry. In the second one here is a value Hall, quantum value Hall effect. So again, they are demonstrating that you can actually create a waveguide where you have bending. So normally as a wave propagates in this kind of waveguide, you would have very strong backscattering. But because this edge state is topologically protected, so it's kind of immune to certain defect. So that's work published in 2017. And this work here published in 2016 is a demonstration of a topological insulator. So which is this kind of insulator is protected by time reversal symmetry. So you don't break the time reversal symmetry.
I'm sorry, I have a question again. Can you comment on the typical length scale which is used in these artificial structures? What is the distance, say, between the?
So yeah, so for this one here, you can see it's about 4.3 centimeter.
Okay, thank you.
Yeah. So it really depends on the frequency. So if you want to, I think this study was done at audible frequency range. So if you want to go higher, you can go smaller scale. Okay, so the one on the far right is related to high order topological insulator. So you can design a lattice and you can get topologically protected corner modes. So that's, there are many works. I'm only able to maybe just pick out 4 of these. And some of these works in this direction are related to elastic waves, so elastic dynamics. This was published in 2015 on PNAS, where they use these objects as very rapid spinning. So they use that spinning. So they use that to break the time reversal symmetry to kind of achieve this churn insulator. So you can see the wave travels along the edge. I think they also here, they actually have a defect here, but the wave is still able to go past it, go around it. So these 3, you can see they are missing the spinning object. So that's creating a defect here.
Ian, I have a question. This is a very elementary question. So usually in the usual solid state electronics, what happens is that we have this single site where electron wave function is localized on the atoms, right? But in this structure, it looks like this, how to say, the pseudo atoms, pseudo site. They have this hole, so it's empty. So how can I understand the localized wave function?
I think this is just black. I'm not sure if that's.
Oh yeah, not this platform, but the previous one, like you showed me.
Which one?
This acoustic high order topological insulator.
This one.
Yeah. So how can these wave functions?
Yeah. So this is maybe I try to explain this way. So these are actually what you see is a cavity.
Yeah.
This cavity, they are connected by small tubes, coupling tubes.
Right.
So you don't see the tubes very clearly in this figure, but that's my understanding. That's kind of mimicking the the hopping between atoms.
Okay. But can phononic wave function be localized inside the cavity?
Yes. Right. Because the cavity, they have their eigen mode.
Okay, I see.
Yeah. So energy is very confined there. Yeah.
Okay, I see.
So so this is now the elastic wave. I think they achieved topological insulator, the edge states. This is an elastic high order topological insulator. Of course, there's also maybe I think there are a lot more work done in photonics than in phononics, but I'm not an expert in photonics, so I'm just gonna show you this slide here. This 2009 paper is very famous. So I think they did the churn insulator. So let's talk about twisted bilayer graphene, right? So the reason I got into this is, of course, 2018, everybody knows that there's 2 back-to-back papers published in Nature that they found the magical angle. So I saw the paper and I was like, because we have this analog between we know there's analog between acoustics and condensed matter physics. Can we demonstrate the flat band at metric angles? So that's what I asked my student to do. So we tried a few months and we succeeded. So basically, for those of you who may not be familiar with twisted bilayer graphene, I think you are familiar with. But anyway, we have two layers of graphene, and you can rotate one layer with respect to another layer. You can create this so-called Moyer pattern. Okay. So this is I don't remember exactly the angle, twist angle for this. But as you apply the twist angle, you can see the unit cell goes from a single honeycomb to a much bigger Moyer superlattice. So in 2011, the Professor Rafi Bestritzer and Alan McDonald, they did this theoretical study. They found that as you twist the two graphene at about 1.1 degree, you actually have this flat band at zero energy level. So this work was demonstrated experimentally by the two Nature papers I mentioned. So Pablo Hilara, I'm not sure if I pronounced his name correctly. Did two studies. One is they found mod-like insulator. The other one is unconventional superconductivity by using twisted bilayer, magical angle twisted bilayer graphene. And they received the 2020 Wolf Prize in Physics because of their work on twisted bilayer graphene. So, and people in classical wave took notice of that, right? So, like for example, people in photonics, this is one of the works in that they use, I think they use waveguides, optical waveguides, to form Moyer pattern, and they use that pattern to localize and delocalize light. And this work here is they apply two hyperbolic metamaterial, optical metamaterial, so one on top of the other one, and they apply a twist. And what they found is that they found this transition angle, topological transition angle. They also call that magic angle, where the equal frequency contour goes from hyperbolic range to hyperbolic to elliptic. There's also similar work in acoustics, and this is a bilayer phononic crystal. So they focused on the value Hall effect. And this paper comes out of Jenny Hoffman's group at Harvard University. So they designed this acoustic structure. This structure is actually not real. This is simulation, but they have a software that can make really realistic figure. Anyway, they have this interlayer membrane that gives you the coupling between the two layers. And these steel rods, as you can see in each layer, it's basically like atoms, so they scatter sound. So they basically demonstrate AA and AB stack bilayer acoustic graphene. They did this column source simulation, which is they simulate this real structure, look at the band structure, compare that with the tie binding model. They found very good agreement. Okay, so I'm going to talk about what we have done in this direction. So this is sort of the outline. I'm going to first talk about photonic crystal, and then I will talk about phononic crystal. So we started off with a monolayer photonic crystal, or photonic graphene. So basically we have a honeycomb lattice of metallic cylindrical rods on metallic plate. What this structure gives you is you have confined modes on the surface. These are the spoof surface plasmons. Okay, so it's a microwave range, so gigahertz. So because of this certain lattice here, we get a direct cone at the K point, which is not surprising. And we actually did experiment in collaboration with Nanjing University. So they made a sample, and we first measured the monolayer. So there's a very nice agreement between theory and experiment. But again, this is not new, right? It's monolayer. And then we went on to build another sample, and we kind of stacked them together. So that's what the sample looks like. And there's a gap between them. And that gap, the air, is the kind of the coupling medium for the two layers to interact with each other. So that's kind of introducing interlayer coupling between them. As you can imagine, if the distance is bigger, you have a weaker coupling, interlayer coupling. If the distance is smaller, you have a stronger interlayer coupling. So the advantage of this platform is you can very easily manipulate the interlayer coupling strengths. I don't think that's something you can easily do in bilayer graphene. So I think that's one of the advantages in this platform. So this just shows you.
Can I ask a question?
Yes, please.
About this coupling interlayer. So probably when you kind of come very close, there is the maximum that you can reach. So how is this maximum compared to the just in one layer couplings? Is it of the same order, or
in one layer there's no coupling? I'm not sure, because we're talking about interlayer coupling, right? You need to have two layers, right?
Yes, but I mean, in the tight binding language, you would have hopping within one layer and then hopping between the layers.
Right. So yes,
what is the kind of order of magnitude? Because the interlayer one you can change, right? But you are limited somehow when you come close together. So what is this maximum?
What is the maximum interlayer coupling? We have a, maybe I can, we have a figure maybe in a few slides, maybe I can, where we vary the distance between them. We don't go all the way down to zero though, because we didn't think that's very useful. But certainly there's a limit, right? There's a limit where you cannot go any closer. Yeah, but there's a slide. So
okay.
Tell you a little bit about it. And there's a question from Alexi, I think.
Yeah, I mean, it's actually Dylan asked a very similar question, so I'll still repeat. Can you reach a situation where the coupling between the layers is stronger than the coupling inside the layer?
Oh, I think that's a good question. In theory, I think so. We can design. I don't know about for specific photonic design, but for phononics, I think we might be able to manipulate the coupling in a way that the interlayer coupling is stronger than in-layer coupling. So if there's anything interesting about it, we'd be happy to discuss that.
Okay. Yeah. Thanks.
Yeah.
I have a follow-up on these questions. What do you mean by coupling, actually? So let's take one of these structures. So I guess you propagate acoustic waves.
Oh, this is photonics, so microwave.
Microwaves which propagate, so to say, along the
2D plane. So they are
yes.
They are confined on the surface. Yeah.
Right. Now, normally you would have, if you have only one layer, then you would have to somehow close it right from the top, so that these waves propagate in the cavity and do not run out. So
no. Actually, for this monolayer, you don't have to close it, because the wave basically gets trapped on the surface. They propagate into the air in the exponential way. It's evanescent way. So
the wave itself, you say, propagates inside the 2D, well, this kind of
yes.
substrate, in the substrate.
Right. Substrate, yes. It's engineered surface.
I see.
Yes.
Okay, thank you.
Okay, thank you.
But still, I have a question. How do they?
Sure.
How does the coupling? What's the coupling? What's the physics of the coupling? So
yeah,
now I have a wave. So is that this evanescent part of these waves which
yeah,
start
so in both layers you
I
have evanescent wave, and they get coupled. So yeah.
I see. Thank you.
Yeah.
Alexei has still raised hand. Alexei, do you
Oh,
have
okay.
a question? Okay, I guess he didn't have, he just forgot.
Okay. Okay, so so this just shows what AA stack and AB stack look like. I don't think I need to talk about this one because I think you guys are all familiar with this, but this is the band structure for AA stack. This is band structure for AB stack. So for AA stack, you have this kind of 4 crossing points. For AB stack, you have these 2 bands touching each other. So we started with just building AA stack and AB stack in photonic crystals. And we use finite element method to simulate the band structure. The type banding is solid line, and the circles are from numerical simulation. So of course we try to fit the type banding model, but in general we can have a pretty good agreement. This distance between the first band and the fourth band, we call it 2 delta F, and this is, I don't know if I have here, is related to the interlayer, vertical interlayer coupling, hopping strength, gamma 1. So we actually did a study where we changed the distance between the 2 layers from 18 to 32 millimeter. As you can see, when you have a smaller distance, starting from 18, you have a larger interlayer coupling strength, gamma 1. And because we plot this, the y-axis in logarithmic scale, and you see a straight line, that means this coupling strength is actually exponential function of the distance, which is expected because we have an evanescent wave, which is exponential in nature. And we did the measurement for AA stack and AB stack. I mean, this time we were not able to get as good agreement as we got in the single monolayer case, but I think we still capture some of the features of the bilayer photonic graphene. So next we decide to apply a twist, right? So the Moore pattern is, in order to calculate band structure, we had to have a perfectly periodic structure. And the Moore pattern only becomes perfectly periodic at the so-called commensurate angles. And here's the equation to calculate the commensurate angles. The n and m are integers. So our strategy goes like this, right? For us, it's very difficult to study the band structure at very small twist angle, like close to 1 degree, because the unit cell becomes so large, and it's just almost impossible computationally, because we want to model the real structure rather than type banding model. So what we came up with is that we are going to fix the angle, the twist angle, at a certain commensurate angle, at a large enough angle that we can handle, but it's also small enough. So it's 3.89 is the angle we chose for this study here. And what we did was we varied the interlayer coupling strength, okay? Until we model the band structure at each different interlayer coupling strength until we observe the flat bands, okay? And at that coupling, interlayer coupling strength, we say, okay, this 3.89 is the magic angle for that specific interlayer coupling strength, or the corresponding thickness of the air. So here I'm showing you 3 different band structures. One is at 18.6, that's the air gap between 2 layers, and 20.4 and 22.2. So as you can see, this one here is we got pretty good flat bands. I'm not sure exactly what's going on for this one here, but later on when I show you the acoustics, looks much cleaner than this one. But we do see the evolution of the kind of the band structure going from something not flat to being flat, and then being non-flat again. Okay, so this is something we expected to happen. We also look at the eigen mode at this point here. and this point here, and this point here. So a lot of people ask me, what can we do with flat band in classical waves? So the first application is that you can trap energy at, you can confine energy at certain locations. That's a very good application, especially I think for optics, you can enhance nonlinearity, right? So I think that's a lot of people are kind of pursuing that direction with a flat band photonics. So we also try to study this, and theoretically, we look at the bandwidth of these bands, and there's a equation I think that was derived, was shown in a PIO paper. I forgot the name of the paper. Since like the origin of metric angle, maybe that paper, but they provided a equation to predict this bandwidth here, and so we basically just directly took that equation, and so that's a theory, and we predicted how the bandwidth would vary with the thickness. In other words, the interlayer coupling strength, and we got this red curve here, which is at 3.89. And later on, we also studied a slightly larger angle just to show that doesn't just work for this angle, right? We can do any commensurate angles. This is 4.41. We also have a reasonably good agreement, and yeah. So,
so I have a question. So
yeah,
it looks like if you want to go to like a lower angle, smaller angle, then the size of a unit cell will be bigger and bigger, right? So
yes.
I guess there is somehow physical limitation about your realistic experiment, because your whole system size should be like, in principle, be infinite, but you cannot make it.
Yeah. So we didn't do the short answer. We didn't do experiment for metric angle because we don't think it's possible. It's just the sample is going to be so large.
Okay.
So yeah, so we only did experiment for A, B, and A stack. I think we can still handle.
But in terms of the wave feature, do you think what would be the physical limitation in achieving the largest system size? So let's just say you can prepare largest sample as much as possible, but what would be the physical limitation?
So I think for the AA stack and AB stack, for these samples, I think there are like maybe radius or diameter is maybe 1 meter, and already get very heavy. But of course, this is for microwaves. I don't know if for people in the optics, maybe they can do nano fabrication. They can. I think it's still very challenging. Yeah, actually, I spoke to a group from Harvard. They also published a paper on metric angle photonic. So they also told me it's very, very hard to make samples that can show metric angles, just because the unit cell is so large.
I see. Okay.
That's a challenge. Yeah. So
allow me to ask just another question.
Sure.
Again on this, what is because I somehow missed that. So what is the material
Oh, this is just metal. I think it's aluminum. I think it's aluminum. I don't know if my.
And how thick is this plate? This 2D plate. So the wave itself. Where are the? Because somehow I still don't understand this. The wave is in the air or in the bulk of the plate?
The wave is in air, but
in the air, right? It's trapped between these rods there, right?
Right. Yes.
I'm still puzzled. Now I'm again puzzled, and I don't understand why is it not running off? Why isn't it evaporating?
Why is it what?
Why is it not just running off into the air and going to the Mars or the Moon or I don't know what?
Yeah, that's a good question, because this is called a spoof surface plasma. So these intrinsically they are surface wave. So they get because of this kind of engineered surface, right? If you have a surface, right, of course the wave's gonna go all the way into air. But because of this, maybe if you look at this band structure, actually, if you look at the band structure, see it gets very, very flat here. That means the group velocity goes to very, very slow. Okay, so the energy gets sort of trapped on the surface of this metallic plate.
Okay, thank you.
Yeah. So, and okay, so we also studied, later we studied a larger commensurate angles. There are two cases that we looked at. One is SE sublattice exchange with SE even. The other one is called sublattice exchange with odd symmetry. In this case, the rotation angle is about 38 degrees, and this one is about 21 degrees. But if you look at this case here, there's a 6-fold symmetry. I think that's why it's called evens, SE even lattice. This one has a 3-fold symmetry. I think that's why it's called SE odd symmetry. So we also looked at the band structure. We actually also did experiment for this case. This is SE odd. So this is almost like a AB stack, but it's happening at much, much smaller frequency range. And we also look at the Poynting vector. So this shows you how what the energy flow looks like. So they're kind of going in two different directions at C1 and C2, these 2 points. This is the SE even, okay? And we see there's a small band gap. This band gap turns out it's topological. But we also plotted the Poynting vector. So I'd like to get into this band gap, and actually this work is inspired by Dr. Park's work in PRL. So we actually saw the paper, and we were like, maybe we should also try this corner mode, right? So we look at this is the whole band structure of SE even. Okay, so we zoom in here, and then we further zoom in here. So we have this very, very small band gap, okay? And we basically, I think there's certain procedure to look at whether this band gap is topological. So basically we look at there are 14 bands below this, below this band gap, and we count the so-called eigenphase. At gamma point, there's 7 that is -1 and 7 that is +1. For M point, there's 8 and 6. So there's a mismatch between gamma and M. And that is indication that this band gap is topological. So we built a large scale sample, not experimentally, but just in simulation. Again, this is a very large sample. We didn't think we can build this in reality, but we did the eigenfrequency analysis. We found there's a eigenmode within the band gap of the S even sublattice. And we look at the eigenmode, you can see the 2 corner modes on both sides. We also try to look at whether this is indeed topologically robust to defects. So we remove a corner here, a small corner, and we look at the eigenmode again. There's still a mode within this topological band gap. And so the corner modes are still there. So it's sort of robust to defects. And I just wanted to mention that at the same time, when our paper got published, there are also 2 other works that got published on the same topic. This one on Physical Review Letter. They use a nano silicon disk to achieve to build the photonic crystal. And this is the group from Harvard, Eric Maser. And so they use a silicon, I think, again, silicon for the photonic crystal. They're working at much, much higher frequency. This work is also, these 2 works are purely simulation. There's no experiment. So I think experiments is going to be very, very challenging. So let me move on to a phononic crystal. So I would just maybe speed up a little bit because in this case, a phononic crystal is a very similar idea here. What we do is we take a plate and we drill holes on the plate, okay? So you think of all of these as cavities, okay? What happens is that you can also create a kind of acoustic surface wave. And the waves propagate in the air right above this plate, but it gets trapped on the surface of the plate. So they don't propagate into air. They get trapped on in the air close to the surface. Again, you can see that because the band gets very, very flat. So the group velocity is very, very low in this case. So we call this a spoof acoustic surface wave. Again, this is a monolayer, so we can have, not surprisingly, we can have a gamma point at K point, a gamma direct cone at K point. Now we can just naturally build bilayer structure by just stacking up two plates with cavities. And this one is AA and the other one is AB. Again, this is, we have seen something similar to this in photonic crystals. I'm just going to speed up. This is AA stack, and this is AB stack. Sorry, this is AB stack. So we compare the simulation with tight banding model. Again, the distance between the first band and the fourth band is related to the interlayer hopping. And so this just to emphasize, this distance here is corresponding to the vertical interlayer hopping strength, gamma 1. Here's the tight banding model that we used. I think some of you are very familiar with this. And I have also actually thought about, you have we actually in our model, we assume gamma 3 and gamma 4 are 0. But I think with acoustics, we can even manipulate the coupling strength so that gamma 3 and gamma 4 are much greater than gamma 1. So that's something we can do if there's new physics there. We also look at, similar to photonic crystal, we look at how the coupling strengths change as you increase the distance between the two layers. So again, as it become further apart, the interlayer coupling strength becomes weaker. So we built the twist bilayer phononic graphene, and we looked at we use the same equation that I just talked about to predict where the magic angle, sorry, not magic angle. We fix the angle at 3.481, which is not a commensurate angle, but we vary the interlayer, the distance between two layers as a way to vary the interlayer coupling strength. And we use this equation to predict, okay, at this thickness, we're going to have a flat band. Okay, and this angle 3.481 becomes a magic angle. So indeed, at this angle, we vary three results here: 14.2 millimeters, 15 millimeters, and 15.8 millimeter. I think this result looks much cleaner than the photonic case. But, we have a very flat band here. So this 3.481 becomes a match angle for this corresponding interlayer coupling strength. So this is for 3.4, and we also look at the eigenmode. As you can see, when you have flat band, you have very confined energy at the corners. We also tried a large angle 5.0, and you have sort of flat bands, not as good as the previous one. I think as you go to larger angles, it's a little bit, you're going into that very strong coupling domain, and it's a little bit hard to get very clean results. But again, we have a good agreement between prediction and simulation. Okay, so last one is going to be related to elastic waves. So again, we start with monolayer elastic dynamic phononic crystal. This time we are looking at the real surface acoustic waves. So these waves, they propagate in the solid, okay, but they don't go into the bulk. They are evanescent wave, okay. So when you have a monolayer, again, you have this direct cone at K point. So, and we basically, this time we are not stacking up anything. We're just making pillows on both sides. Okay. So there's an interaction between the pillars on one side of the plate and the pillars on the other side of the plate. Okay. And so we tried AA stack. And we have seen this before, so I'm not going to spend too much time on this. And AB stack, also the band structure is similar to what we see in electronic materials. Okay, and we also tried the SE even, 38.213 degrees. Again, we have seen this band structure before. We have this very small band gap. Okay, so this is what we call weak interlayer coupling, because here the thickness between the thickness of the plate is, oh sorry, it's not written here. It's a 2.5 centimeter, so it's pretty thick. We also try to look at strong interlayer coupling. So we make the plate much, much thinner. So in this case, it's 3 millimeters. So the two layers are now much, much closer. So there's much stronger interlayer coupling between them. So we want to see, okay, can we have some new physics in this case that maybe do not have counterparts in electronic materials? And we are very interested in that. So in fact, we can actually, the reason we chose the 3 millimeters is because we have this accidental direct cone. This should be K, not X. We actually have this accidental direct cone at K point. So this is something, not necessarily protected by the symmetry. It's accidental. So it only happens at this specific thickness. And we have this unit cell, right? So what we wanted to do is that if you see this 3 triangles, for example, this one include this 1, 2, 3, 4 circles or pillows. And this triangle contains these 4 circles, and same thing for this triangle here. And we have another 3 triangles which each one contain another 4 pillows. Okay, so what we do is that I want to open up band gap. I want to break the degeneracy at the direct cone. Okay, I want to create a topological band gap. So I break the C6 symmetry. Okay, by rotating these the lighter color triangles, rotating by 3 degrees in the counterclockwise direction, and the darker color triangles in the clockwise direction by 3 degrees. The other case is I'm doing the opposite of that. So it's -3 and 3. Okay, so this band structure corresponds to this case here. So because I break the C6 symmetry, now I open up a band gap here. This one is without breaking the C6 symmetry. So we have the direct cone. This is the other case where we kind of rotate the pillows in different directions. We also have a band gap that is opened up. They look almost the same as this one here. But if you look into the eigen mode, for example, if we pick this point at the edge of the band gap and pick another point at the lower edge of the band gap, and we look at the eigen mode. So this is one for the top one, and this is one on the bottom, close to the bottom edge of the band gap. Okay, and then now we look at this band gap here. So similarly, we look at this point and the point below it, and you can see that this one, there's inversion, band inversion happening here. So on the left side, this eigen mode, it got swapped to the down below here. And this one here got switched up to this one on the top. So there's a band inversion here. And because of that, we think we have a value Hall effect here. So we create this 2 domains. One is this one, the other one is created by this kind of structure. And there's a zigzag edge state between them. So we take this supercell and we did the band structure. You can see we're plotting the outer plane modes. Okay, you can many dots, but some of the motions are in plane. We don't care about the in plane movement vibration. We only care about the outer plane vibration. So this state, this mode here is eigen mode, is edge mode, and this is not edge mode here. You can see the movement. This mode is traveling from right to left, and this mode is traveling from in the other direction. Yeah. So we created a kind of defect, what we call 60 degrees here, and we allow the elastic wave to travel along this edge state. Sorry, And normally, if you have a just a regular waveguide, when the wave meets a defect like this, you get a huge amount of backscattering. Okay, but in this case, because the wave propagation is topologically protected because it's a quantum value hall here, so you have this very robust wave propagation along this waveguide. So I think just kind of summary, we have demonstrated that analogs of bilayer graphene, we have talked about different types of AA stack, AB stack, SE even, SE odd, and magic angle. They can all be realized in classical wave system using either photonic crystal or phononic crystals. There are, of course, what we have not seen is experimental demonstration of magic angles in classical wave system. But the question is that really necessary? Because I think classical wave system is very easy. We can manipulate lattice very, very easily. We can do Kagome lattice, right? You can also get flat bands from Kagome lattice. You don't necessarily need to have two layers, twisted bilayer structure to get flat band. So I think that's a question we have to think about. Where do we go from here? I think there are opportunities. Certainly, I think what we can do is we can certainly leverage the interlayer coupling strength because we can manipulate that, and we can also take advantage of twist angle. Both of these at new degrees of freedom to, hopefully we can discover new physics that do not have counterpart in quantum materials. I think the value hall due to the strong interlayer coupling in the elastic metal material, that result, I think that's kind of like the first step towards that direction. So can we go beyond the analog of bilayer graphene? That's what we are interested in. So I think with that, I will thank my sponsor, NSF and Penn State Startup. And I will take questions. Thank you very much.
Thank you, Professor Jing, for this excellent seminar. Let us thank our speaker. And we are open to questions.
I have a question, Yoon. So this is more about conceptual things. So so probably the reason why condensed matter people were interested in this twisted bilayer graphene was probably this strong correlation effect where superconductivity and things occur. So I guess the probably naive analogy is the probably non-linear effect that occurs in this classical wave. So do you think if you make a flat band, then that means group velocity is 0. So do you think then this higher order non-linear effect would be somehow enhanced in this flat band?
Yes. So I mentioned that I think one of the applications is that when you have flat band, you can certainly enhance non-linear effect for classical waves. But I guess the question is, if we can, because we can manipulate lattice very easily. The question: do we have to use bilayer? We can use monolayer to get flat bands. You probably know other lattice, right? Like Kagome lattice, you can do flat band from there as well. So I think that's really the question we have to address. Why do we take extra steps, walk extra miles to make bilayer structure to get flat bands? But I think one of the selling points is probably that these magical angle flat bands are topological. I think that's probably an advantage. I don't know how that benefit application for classical waves. I have to think about that. Yeah.
So another question is probably also more basic because I have basically zero knowledge about this engineering. So do you think there is like a motivation about this searching for this strong correlation in electronic system? Do you think is there like an engineering benefit about this triggering nonlinear effect in this acoustic metamaterial, or
is there
like some engineering motivation to like enhance the nonlinear effect in this acoustic metamaterial? Or
I think in optics, I know people talk about this enhancing nonlinear effect. I don't know because I'm not an optics expert, so I don't think I can comment on that intelligently. But for acoustics, it's very difficult to get nonlinearity unless, especially at audible frequency range, unless some pressure level is super high.
Okay, I see. Okay.
Yeah. But I think when you have flat band, you have very high energy. What is it? Energy density of state, right? I think in acoustic, I think that is related to the emission of sound. So if you have imagine that if you put a source in the material in a place where you have very high energy density of state, I think that would also enhance the emission of sound. So enhance the source, that's like a speaker. So I think that's actually one of the applications we try to pursue with this design. Yeah.
Okay, thank you.
Yeah, thank you.
We have a question also from Sergey.
Yeah, first, actually two, or question comment. Question first, what about attenuation and losses, especially when you compare your photonic devices with the phononic devices?
That's a great question. Actually, our phononic paper, we submit to PRL first, and it was rejected by a reviewer, and it's precisely because the loss is an issue, especially for these spoof surface acoustic wave. They have very strong energy loss. However, that's not a issue for the photonic crystal. They in the microwave, in that case, the wave does not decay that much. So I think it's more of a problem for acoustic waves.
So can you give us an idea in terms of some, I don't know, quality factor or whatever to get a feeling what we are talking about here?
So yeah, so let me see. Can go to, the reason why this problem is so unique in acoustics is because so there are cavities here, and when the wave they interact with cavity, there's a very strong thermal viscous loss. Okay, and unfortunately, these waves can only be excited at almost close to the resonant frequency. So you have resonance frequency, resonance, and the loss. Then the resonance is going to amplify the loss. So what happens is, my estimation is that maybe if you have a wave traveling along this direction, maybe after 20 cavities, the energy is gonna decay for maybe 90%, maybe 80%. It's gonna be a quick decay. Yeah.
Okay. And how does that compare to your photonic, to your photonic devices? Photonic. So 20 here, it's 20, and there 200, 2000, 20,000, just to get an idea.
For photonic, because there's no such thing as a thermal viscous loss. I mean, there's certainly a loss, for any wave, right. But we have not observed a significant amount of loss, at least for A, B, and A stack. We have very large sample, and we were still able to get pretty good measurement results. So the loss is not a major concern in our photonic graphene design. I don't know any quantitative number for the loss in that case, but it's usually a major concern. Yeah.
Right, and just a comment adding to Munjib's question about nonlinear effects, which sure will become maybe important if you have, if your linear part of your wave equation is, so to say, dispersionless. But what you are interested in the case, say, of superconductivity is that you want to rise, you want to make the transition temperature larger, and then you think about how that is related to the material properties. And then maybe one of the ideas is that an almost flat band is good because the kinetic energy is small and the interaction energy is bigger, and so on and so forth. But it's a long way maybe to still prove that that will lead to higher transition temperatures. But here's a bit different. In the case if you add nonlinearity, there is a number of studies what happens when you take waves in flat band systems and then you add nonlinear terms. So what you can expect, one of the things you can expect, the constructive things you can expect is that nonlinear terms in your wave equations will allow you to additionally tune say energies or frequencies of your states by just varying the amplitude of your state.
Okay.
And the flat band at the linear level may allow you to still keep these states non-dispersive or weakly dispersive.
Mm-hmm.
So probably that's what I see is the most useful thing which may come out of, in general, out of adding nonlinear terms to flat band wave equations at the linear level. But there might be other interesting aspects.
Okay, thank you for the comment.
Okay, do we have any other questions or comments from the audience?
Thank you.
It seems not. So in this case, let us thank our speaker again. And with this, we